Hello, good morning, and welcome to our virtual showcase 2020. We are here today to give the presentations for the track 5 projects that we have. And I'd like to welcome all of you. And I think this is going to be a pretty exciting morning today. We have all the participants who are here, and they'd like to share what they've done over this period with you. We all know that unfortunately we couldn't get these projects completed because of the coronavirus epidemic and the school was closed. And a lot of these folks, their hard work was actually all stored in the school, or they had some parts with them. And that's where it got left out. So, but they'll tell you exactly what they did and how interested they are. And we shall get on with these, with their particular um, their description, and they'll tell you about their projects one by one. So what I have is I have the first project, which is called the Wheelie Walker, and this was we think of some wheelchairs, wheelie walkers, and wheelchairs. We sort of associate them together, and for people, and we associate them mostly with people who need help or are handicapped or are old. Now, this product fulfills an acute special need in society. You've seen wheelchairs of all kinds, but I don't think you've seen one like this because this one is a special kind for a special need. So, with that said, what I'd like to do is I'd like to welcome I'd like to first ask the members of the wheelie chair walker to please raise their hand so that they can be counted and you can be put into the system. So if that is okay and you're all kind of in, what I'd like to do is I'd like to invite the first member who's the team leader, Juan Martinez, if you'll please come on and get the meeting started. Juan, go ahead, Juan.
Good morning. Can everybody see me and hear me okay?
You're looking great.
All right. Well, thank you for being here this morning. My name is Juan Martinez. I'm the team lead for this project. Our team lead is Daniel Reyna, and the rest of the team members are Eya Dusuki, Meta Wasid, Min Lee, Ken Yu Yang. Our faculty advisor on this project is Professor Sharma, and the project was sponsored by the Department of Mechanical Engineering. So for this project, we decided to work on our design that will impact other people's lives. We know that wheelchair users, they face many challenges through their daily lives. Simple tasks as trying to reach an item over a counter and using a microwave are pretty simple for a person that has walking capabilities, but for a handicapped person, it's pretty hard to do. In addition to these challenges, there's some health problems associated with using wheelchairs, such as poor blood circulation, back pains, and some of them might have some kind of depression. There are some wheelchairs out there that actually gives the users the ability to perform this task. But as you can see, some of the wheelchairs are bulky, are heavy, and expensive. During the physical therapy, patients using walkers they need constant assistance, and as using a walker, it requires a great deal of upper body strength. And some of the walkers, or mainly all the walkers, are not hands-free. The Wheelie Walker is a combination of a wheelchair and a walker into one. Our design will improve the user's health by providing better blood circulation. It will give them back the personal mobility. It will give them back their independence. Our design will allow the user to use this device hands-free and only using their lower body support. The three main features on this design is the exoskeleton, that is attached to the wheelchair, and the gas system lifting mechanism that is attached to the kinematics, and the quick release axle for easy transport for this chair. The quantifiable objectives on this project is the weight limits on the individual. We set it to be 220 to 240 pounds max. The weight of the chair was important. It needed to be between 30 pounds and 50 pounds. And the cost to the user needed to be between $4,000 to $5,000. Non-quantifiable objectives on this project, it needed to be lightweight materials. It will need to provide some maximum comfort for users, and it needed to be easy to service by replacing parts if needed. Now, the way that we approach the project, we broke down this big project into little pieces, as you can see in this flow chart. The idea was validated by interviewing wheelchairs users and professional physical therapists, and we got a lot of pretty good feedback that we were able to incorporate the feedback into our design. So the chart was to identify potential problems and constraints throughout the project, and also to determine the resource and knowledge required to accomplish the milestone. Now I'm gonna hand it over to Daniel, who's gonna talk about the design calculations.
So a couple of basic design calculations that we needed were to determine the moment about the axle, which would help us determine if the wheelchair was stable in the upright position and wouldn't tip over with an individual sitting in the chair. And also we need to calculate the force needed to lift an individual up into that upright position. And based off of some information that we researched, 240 pounds was the number that we settled on. So this is just some of the variables that we used. And here are the equations. This is just to give you an overview of what we used to come about that information to determine what we needed in order to make this work. And like Juan mentioned, our main feature is our exoskeleton, which is essentially a KFO leg brace, knee ankle foot orthotic brace that goes up to the, if you look at the diagram, it goes all the way up to the thigh, which is very close to the hip joint, which allows for a lot of stability for the user. Also, these types of braces have an adjuster. As you can see in the bottom left corner is a zoomed in image of one, and this adjuster allows the person to adjust how much mobility they have at the knee based on their own strength and their own capabilities. And as the idea is, as they get stronger and more able, they can adjust that to be more freely moving all the way to about 90 degrees. In this case, this one goes to 120. Using this will allow the user to be supported when the upright position, be able to actually walk with the chest support as well. Now I'm going to turn it over to Aya. She will explain to you our lifting mechanism.
In order to create the Wheelie wheelchair, we need a lifting mechanism. Here we have a picture of the lifting mechanism that will be used for the wheelchair. The gas springs will be attached to the chassis connecting to the upper frame of the wheelchair. The user will simply press down on the button to activate the gas springs to lift the wheelchair from a sitting to standing position. Another important feature we added to our wheelchair were quick release wheels. Now, there are two types of tires that can be added onto a wheelchair. Pneumatic tires, which are similar to a bicycle tire, and a solid tire. Even though the initial cost to purchase an air tire set is cheaper than a solid tire set, because it has an inner tube filled with air, this means that it's required to be changed every 2 to 3 months due to deflation. By choosing to select solid tires, this helps reduce future costs. The quick release pins allows users to easily pop on and off their wheels by pressing on the button that releases a spring pressure, locking the pin into place. This helps resolve the issue of the weight and bulkiness of the wheelchair. Now Meta will share a few of the drawings that were created from our design.
For drawings, we use an ASME standard. Some of our drawings were sent to be fabricated to be manufactured. Here is our chassis and what we sub-assembly, the anti-tip axle. Here's the chassis side with welding information. And this is our bill of materials. It lists the manufacturer and purchase parts, and it includes the part number, description, and quantities. And now Juan will talk about the manufacture planning.
During the planning on this project, we track our progress and completed tasks using Gantt charts. We broke down the project, as I mentioned before, and we assigned team members for each phase of the project, and they were able to use the Gantt chart we created to track the progress in percentage, as you can see in this picture. This is just to show the progress as of March 13. This is another view of kind of like how we plan it all the way to the end, to the testing feature, to the testing process throughout the project. And now Khan will actually talk more about the manufacturing process required for this project.
So this wheelchair requires 4 manufacturing processes. There are tube cutting, tube bending, welding, and assembling. So in the machine shop, we make the chassis, backrest, and the handle assist. We also use the abrasive water jet machine to cut some small and complicated parts. After we gather all the necessary parts, we will use the digital caliper to make sure every part is within the allowed tolerance. For the assembly process, we will connect the individual part by using groove, and we will connect the frame into the wheel. We also like testing if it had any potential problem. This is a picture of the lower chassis, rear wheel, and front wheel that we make on March 13th. After the prototype complete, we will perform the following testing operation to ensure the quality and safety of the wheelchair. Is it the appearance, quality, workmanship, measurement, functionality, environment use, and final product evaluation? I will hand it over to M. She will talk about our budget for this wheelchair.
So this is the table showing our status for purchase items. Up to now, the majority of all parts we need for the project have been ordered and delivered, except for the exoskeleton. The reason is because the exoskeleton is shipped from overseas, and the current pandemic make the delay from the delivery process. So until now, we haven't received it yet. This is the only issue that we met for this project. And this is the 2 tables comparing the initial budget at the beginning of the project from last semester and the actual cost for our project. And the total gonna be $2,695. And you can see we're good within the budget. And now Daniel will talk about the overall project status.
So basically where the project was left off at, we, as you can see, based off these numbers, we pretty much had everything fabricated and ordered. Like we've been saying, the exoskeleton is kind of the only thing we hadn't really received yet. And we had started test fitting and assembling our parts to get our prototype together. So we were pretty on track in the assembly stage with this design. Now, despite what everything going on, we were able to have what we felt were some successes in this project. A big part of that being the overall design of the project, as well as purchasing and manufacturing parts as if we were some company trying to build this project, working with other vendors. Unfortunately, we were unable to finish the full prototype prior to the campus closure, as all of our parts were left on campus the last week. And at this time, I'd like to open up to any questions that anybody might have.
Well, the first group for the Wheelie Walker, well, thank you very much for your presentation. All right, well, welcome back for our second presentation. Let's look at it from this point of view. We've all moved in our lives. We always move, maybe homes from one place to another. Businesses move, from one place to another. We live in small homes, large homes, buildings of all different kinds, multi-storied to say the least. but moving has always been associated with a lot of work, and especially when you have to move stuff, upstairs. Uh, so this particular problem has been taken by this team, and they have found a solution for it.
Hello everyone, my name is Hamad Arabah. I'm group leader for our team. Our project is called Stair Climbing Trolley. There are 5 people in our group: Adel Katan, Nasser Al-Buraiki, Faraj Al-Hadri, and finally Ali Khaja, who's the co-leader, and who also will start with the idea of our project.
Hello everyone, my name is Ali Khaja. I'm the co-leader of this group. So basically our idea is a cart that can carry heavy appliances up the stairs. This device would satisfy the need of movers who are subjected to heavy lifting and often develop a chronic back problems, and students and old people as well. We are targeting moving companies and big stores such as Home Depot and U-Haul to run this device. We did some online research before going on with our idea, and we did not find a similar device that is fully motorized. So we decided to conduct a survey to determine the need of such a device. We conducted a survey and we received 160 responses from anonymous people, as you can see. We asked a few questions, such as if you would buy such a device, and 96.2% answered by yes. We asked if you rent such a device, and 96.9% answered by yes. And we also have received a great feedback. And now Nasser, my teammate, will briefly describe our project.
Good morning, everyone. My name is Nasser Al-Buraiki, and I'm going to give you a brief description of our project idea. Our project is a stair climbing trolley. It's carry heavy loads up to 330 pounds up the stairs, and it's motorized and can be operated by one person. And it has a speed controller to adjust the speed and control the movement. And it carry weight on a rough and flat surfaces. And it's absolutely safe and easy to handle. And it has a designed tri-star wheels to climb up the stairs. And for the project development, we brainstorm our ideas and we draw 2 sketches. The one on the left is a 2D view of our trolley, and the one on the right is a sketch layout of our trolley base. And now my teammate Adel Qattan will talk about the scope of work.
Hello everyone, my name is Adel Al-Katan. Today I'll talk about the scope of work and sample calculation. For the scope of work, we divided our project into 7 phases. 4 of them were in the first semester and 3 of them in this semester. For the first semester, the first step that we did after our idea got approved is setting a timeline to complete our project. After that, we scheduled a weekly meeting. Then we started designing our project and we made our parts on SolidWorks. For the second semester, we were supposed to make a prototype test. Then we were supposed to produce a working model in our showcase. Now I'll talk about the sample of calculation. Here's a sample of calculation that we did for the climbing motor. And here's for the other motor, which is the driving motor. And here, as you can see, is a summary that shows the differences between the 2 motors. So for the climbing motor, the power needed is 1500 watts, while the driving motor needs only 770 watts, which is almost the half of the power of the climbing motor. For the torque, the climbing motor needs about 530 Newton times meter. The other motor needs only 37 Newtons times meter. We assumed the efficiency for the climbing motor to be only 70% because it's a hard task for the climbing motor. And on the other hand, we assumed the efficiency for the driving motor to be 80% because it's an easy task to move the heavy objects on the ground. And now I'll let my teammate Hamad to talk about the changes and improvements.
Here are some of the modifications that we did. We successfully managed to reduce 40% of our cart weight by making holes, as you can see. Our cart consists of three assemblies. Two major assemblies, as shown. The bottom left one is the handle, and the right bottom one is the base. And, those two are welded together, assembled by welding. And the top right is our tri-arm, which will be bolted together. This is how our cart should look like when we assemble it. As you can see, it's 50 inches in height to make it accessible for most people. And now Doage will share with you our purchase parts.
Hello everyone, my name is Doage, and now I'm going to talk about the purchased parts and the manufacturing process. Starting with the purchased parts, we purchased 5 10-18 mild steel sheet of metal with 5 different thicknesses, as you can see. We purchased the rear motor controller, 4 12-volt lead acid batteries, potentiometer, and the chain. We also purchased the front motor bearing, 12 bolts and nuts, a machinable bore sprocket, washer, and split washer. So for the manufacturing process, we bought 5 sheets of metals with different thicknesses, as I mentioned, to make our parts using plasma cutter. In order for the machine to cut the sheet of metal, we needed to make AutoCAD 2D files, and then the machine will start cutting automatically. We finished 95% of the parts requiring plasma cutter. We only had one part left, which is the C channel, and then we were supposed to start the welding process. For the fabricated parts, we finished fabricating the bearing housing. We were working on fabricating the main shaft. Then we were supposed to start working on main shaft sub-assembly, as you can see in the picture. And now Ali will continue with our project status.
So this is our project status before the start of the pandemic. As you can see, green is for done, yellow is for pending, and blue is our next step. We managed to complete 65% of our project, and we were on the right track. We ordered 90% of the parts, and we finished manufacturing all parts requiring plasma cutter. We started the fabrication process and finished few sub-assemblies. As you can see here, this is our Gantt chart. As you can see, it indicates the task of each group member. We revised and checked our drawings. Then we started searching and purchasing parts. Then we started manufacturing using the plasma cutter, and we finished it in 10 days. Then we started the fabrication process, and we were supposed to finish it by end of March. Then we were supposed to start the welding process and produce a working model by April 16th. And we could have had a few weeks to make some final edits before our showcase in May. And now my teammate Faraj will explain the bill of material and the cost analysis.
Hello everyone, my name is Faraj Al-Hajri. I'm going to explain the bill of material and cost analysis. The parts in white we are going to manufacture, and parts in blue are going to purchase them. As you can see, we have 11 parts we're going to manufacture, 9 of them by using the laser cut. Most of our parts we are going to use 10-18 mild steel material, and we have 18 parts that we are going to purchase them. For the cost analysis, as you can see, all parts and quantities are indicated. Our estimate is approximately $2,184, and our budget is $2,000. If you have any questions, feel free to ask. Thank you.
Thank you, group. That was the stair climbing trolley. And this is the time for question and answers. Are there any questions for the group that you would like to ask? Then let's do as follows. If you have some questions to follow, sometimes you would like to know, please send them to the host, and we can maybe address it in maybe a different manner down the line. But we'll definitely make sure that your questions get answered. Okay. That brings us to the end of this presentation. Okay, well, welcome back. And now we're going to do the presentation number 3. Now, you know what? At least I know that we've gone past so many construction sites. All over, wherever you go, there's some building being constructed, some home being constructed, et cetera, et cetera. But few of us really pay attention or we've hardly ever thought of how the building materials, et cetera, actually get to where they're supposed to be, especially in high-rise buildings, right? So this team, it takes a person to be working in them to realize what problems others are facing. And this team has just the solution that would help the construction industry a lot. And I'm sure they would cherish to have something like this. So here to introduce this particular project is the team leader for the rope ascending machine project, and that's Tyler Hildebrand. Come on, Tyler.
All right. Hello, everybody. My name is Tyler, and today I'm with my teammates, David, Daniel, Ala, Aisha, and Connor, and we are here to present the rope ascending machine, or RAM for short. So before we get into what the RAM is, I thought I'd provide a little background about how this idea all came about. Basically, construction sites do not allow workers to carry equipment up ladders due to a safety regulation that requires both hands and both feet on the ladder at all times. Because of this, in order to get material and equipment up to the desired floors, contractors are forced to install temporary stairs, as these ones right here, or they're required to rent or acquire different machinery such as forklifts and stuff like that to get the equipment up to where it is needed. To follow the safety guidelines on workspaces that don't have temporary stairs or forklifts, workers have implemented their own manual rope system in which one worker will climb up to the roof, throw a rope down to another worker. The worker on the ground level will tie off equipment, and the worker above will start manually pulling the equipment up in a hand-over-hand type style. This basically creates potential for long-term health issues such as back problems and slows work progress. So now what is the RAM? The RAM is a remote control operated device that can both climb up and down a rope while carrying a load of up to 200 pounds. Its main purpose is to aid workers in getting equipment up to their desired floors, and hopefully will relieve them of the physical strain when they're doing it the manual way I described before. The RAM utilizes variable speed to accommodate any sort of situation you have, and then prevents long-term physical health issues, and hopefully in the end will save both time and money. Some design functions and features of the RAM. As I'd stated before, it's remote controlled. It's operated through an Arduino. It's able to carry a payload capacity of up to 200 pounds. It can carry your equipment both up and down. The fastest ascending, or with the payload of 200 pounds, it will still be able to ascend at a rate of 1.65 feet per second, which is a lot faster than you could do manually. I mean, you couldn't even pull up 200 pounds manually. It's relatively lightweight at a weight of 25 pounds, so it's easy to move around the job site. You could use variable rope sizes from 10 millimeters up to 12 millimeters. We used a 750 watt DC motor to power the RAM. And then to power this motor, we have an 18 amp hour battery, which should provide plenty of battery life. We have implemented a worm gear design. Through the worm gear, there's improved torque, and worm gears are also non-back drivable. Basically what this means is the weight, the 200 pound payload capacity, is not enough to overcome the shear stress between the gears, meaning that if there is no motor input, the RAM should stay in place on the rope. Also, a pulley system has been implemented. There's 3 pulleys overall, 2 tensioner pulleys and 1 drive pulley. Some safety features. Obviously on job site, safety is a huge thing. So we have gone through some features here that we've added. First being the rubber edge guards. These are to protect both the user and the surfaces surrounding them. Also a gradual voltage drop through the Arduino. So basically once you get off the throttle, instead of instant voltage drop, which would cause the RAM to stop instantaneously and maybe cause the rope to sway, when you let off the throttle, it gradually drops the voltage, so it slows down a little bit slower and more controlled. It will automatically stop on the rope if rope slip is detected. Variable speed allows the users to speed up and slow down when necessary, and distance sensors are also added to the top and bottom to avoid collisions. Now I'm going to hand it over to David, who is going to talk about some of the design features.
So behind that casing and housing, we have our main frame. On the right side, you can see the full assembly of the frame. We have top, bottom, right, left, front, back, and some centerpieces. On the left, we have a drawing of, excuse me, where the pulleys and tensioner rollers will be mounted. They're slotted so the rollers can slide back and forth to accommodate the different rope sizes. Excuse me. Also here is depicted this 1/4-inch aluminum plating. The way these would be manufactured is on a water jet table. Cuts out very precise and accurate to what we are looking for. Going on to our next slide, we have basically our full assembly on the right of what we were able to complete. Please mind the zip ties at the top, as there were some holes that needed to be finished being drilled out. Unfortunately, the machine shop closed before we were able to complete those. On the left is what we were hoping to achieve, and you can see that we have reached our goal. Going on to the next slide, we have our drivetrain. This is going to include the assembly on the right with the battery being the rectangular box. The motor is the cylinder at the top. Attached to the end of the motor shaft is our worm gear, which would then drive the gear over to the right on the shaft. That shaft is mounted to our frame using flange bearings. There's slotted grooves in it for retaining rings to hold everything in place. On the far left, we have our main pulley. That's going to be what our rope will be driven by. All of that was ordered with raw stock materials and to be machined in our machine shop on the campus site. Unfortunately, we were not able to get to that, so we do not have those ones completed. We just have the raw materials. Going on to the next page, we have another depiction of an exploded view of that drivetrain assembly. This one also includes the tension rollers. They're a little bit hard to see because there's so many pieces, but ultimately there's some springs that would be inserted in cups, and that would allow our rope to feed through with adjustable sizing. There's bearings inserted into the rollers that would provide a smooth rolling feature. And again, we have the worm gears and flange bearings depicted in this image as well. Going on to the next slide, we have an exploded view of our tension rollers. Now these would be applying the force into the pulley where the rope would be connected. As you can see, the spring would be inserted into 2 cups. This would allow for adjustment, excuse me, depending on rope size. The spring itself has about 137 pounds per inch of compression, which would apply plenty of force that we're looking to achieve. And now I will hand it off to Daniel.
So in this slide, you can see basically the whole thing put together. We have the frame that you guys saw earlier, and then all the internal components and the drivetrain that's connected. One thing you're not seeing here is the cover, which we weren't able to start manufacturing. Initially, we had planned to use some kind of sheet metal or aluminum, something light. But as we went on, we realized more and more the parts could be made of plastic. So that's what we were probably going to end up doing, just covering it with plastic. And you can see here in this next slide, you can see another orientation of the internals. You can see the tensioner pulleys that David mentioned earlier as the rope enters and then as it's about to leave again. You can also see the rope guides. So you can see as the rope enters the top into that tubing and curves around, you can see the rope guides here, these kind of curved tubes almost. This is another one of the parts that initially we were going to make out of metal of some sort, And then we realized that we could just end up 3D printing. So that's probably what we were going to end up doing. Didn't get there, unfortunately, because as you guys saw, we just kind of finished the frame and we were not able to start assembling the internals of it. In the next slide, I'm going to hand it off to Aisha, and she's going to talk about more about the current state where we're at with everything.
Now I'll be talking about the off-the-shelf part. As you can see, this is the list of the off-the-shelf part that we need in order to build our machine. We almost bought every piece that we need except for the last 4 pieces: Arduino potentiometer, transceiver, and wires, which we already found in Amazon. Most of our purchased part we found in McMaster, except for the battery, which we found in DHgate, and the motor, we found it in Monster Scooter. Now I'll pass it off to Ella.
Yeah, I can take over.
Okay.
So looking at the parts for manufacturing, we have the status of each part on the right there. Most of our raw material was purchased already as explained. And we got to finishing and completing the cutting out on the water jet of all the plates. There were just 2 holes, a few holes that needed to be finished, drilled out and tapped for assembly. We also had keys that would be holding like the pulleys in place to rotate with the drive shafts and such. Those were just purchased aluminum square bars that were cut to length on the bandsaw. Pretty simple process. Ongoing, excuse me, manufacturing for the lathe. You know, we had the parts and we were ready to begin or finishing and manufacturing them, but unfortunately the machine shop was closed. So we were not able to complete those. And then for parts that had yet to be began, you know, we had 3D printed plastic items that we were going to kind of do at the very end because they were relatively easy and we would just be able to slap them together real quick. So again, we weren't able to access the 3D printer anymore inside the machine shop, and we're not able to get to those. Now I'll pass it on to Connor, and he'll talk about the remaining portions.
Hello, everybody. So this is a look at the scheduling for our project and where that left off before the school closure. So as you can see, in most of January, we focused on checking and verifying the accuracy of the assembly and parts to ensure that we were correct before purchasing. And then we moved on to the majority of our purchasing for our off-the-shelf parts and raw materials. And then we began the reimbursement process on many of those things. After that, we started manufacturing in the machine shop, where we started with the plates and framing, and we were able to completely finish those using the water jet machine to cut out the inserts for those things. However, as you can see, our shafts, rope guides, and our pulleys, due to them being more complicated and having to use the CNC, we were putting those off a little bit, and the machine shop ended up being closed, so we weren't able to finish manufacturing those things. As far as assembly, we were able to fully assemble our framing, but as for our drivetrain pulleys, due to us not being able to manufacture, we couldn't assemble. As you can see, this is our bill of materials, and you can see that majority of our off-the-shelf parts were delivered by McMaster, while some of our major components like our battery and motor were sourced from different sources. We were distributed $2,000 budget for our project, and we ended up only using right around $950 for our part cost. So we still had about $1,050 remaining balance for our project. We weren't able to get to the testing phase of our project, but this is the process that we would have taken. So we would have connected our battery to our motor to ensure the battery life optimization and that it can be able to run it. And then we were going to mount the pulley and tension rollers to a wall and then hang 200 pounds to confirm the payload capacity of our internal components. And then as well as hanging 200 pounds from the bottom of our frame to ensure that it would be able to hold all the internals. We were going to assemble the drivetrain to the motor to confirm that it's able to correctly rotate it, as well as adding the pulley and tension rollers to the assembly to confirm that it all works together. Then we would have fed the rope through the entire unit and operated it with no payload to ensure that all the internals are able to correctly grip the rope and ensure that the operation is complete. And then we would incrementally add our payload to our operation to ensure that it's able to control the maximum capacity that we designed for. And then that'll be our successful prototype. Thank you, guys.
Okay, thank you. Any questions for these for this group?
Yes, I do have one question from a viewer. The question is, what is the plan for the control system that would control and drive the motor?
So basically, as you can see right here, you have the battery and then the motor. Right, this is a better picture right here. So you have the motor and then all these drive shafts that go through our framing. So this motor, as it turns, basically the worm gear will be on the end of this right here. This worm gear will spin, and then in turn will spin this one. And our main pulley is attached to this right here. So you can see that right here.
If I can add to that too, I think they might be wondering about like the remote operation. We didn't add it to our slides, but we did have a remote designed, pretty simple features on it: up, down arrows, and emergency stop. That would be powered by 2 AA batteries. There'd be a transmitting end to that, which would then be received on the other end by an Arduino inside the case. Again, it would all be wired pretty directly, going from the battery through the receiver and then into the motor, and that would control the operation. I think that might be more so what they were looking for.
One more question is, what would the cost be to the public?
To the public, I mean, so the normal ascenders, they're actually first created for people, like you would attach the ascender to some sort of harness, and it would actually pull people up the rope or down the rope for rescue missions, or a lot of tree trimmers and things like that used it as well. Those ones are relatively expensive. They're around like $3,500. So we were hoping for something like this. We had a low cost. I think it was around $930 to make. So we were hoping we'd be able to sell it for around like, $1,500, $2,000 in that range.
Thank you. And one last question. And then they said, how would you drive the motor?
So as I kind of explained before, the motor would be driven through this worm gear. So as let's see if I have a better picture. So this frame right here, all of these would contain bearings where the shafts would go through, basically these shafts right here. And as you can see, you have the worm gear on the end of the motor. So as it got a signal from the remote control, this would turn either clockwise or counterclockwise, turning this gear, which is attached to our pulley. So the rope would come down through this guide, around the pulley, touch this guide, and then out this guide right here. These tensioners basically hold the rope tied up against the pulley so there's no slip. And then, so as the motor turns, this worm gear will turn the pulley. And that's basically how it works.
Okay, well, thank you guys. Let's go on to the next project. And this one is the shopping bag carrier. Now, whether you do shopping of necessity, right, or whether you do for fun or for indulgences of all sorts, you really have to carry a lot of weight. It doesn't really matter how it is, especially these days, coronavirus days, when you go to shop, you want to shop in bulk. So for most of us, the materials that are getting transported around are the ones that may be the cause of consternation. So here is a solution that has been found by this particular group, and their project is called the shopping bag carrier. I'd like to introduce the team leader, Muad Al-Hatal, and he'll kind of take it from here. Go ahead, Muad.
Thank you, Professor. Hello, everyone. My name is Muad Al-Hatal, and I'm the team leader of the group. And the co-leader is Mansour Abdul Malik, and the other members are Athman Abdul Hadi, Abdullah Sair, Abdurrahman Fadiri, and Mohammed Mansouri. Okay, let's get started. The project is about the design of a motorized shopping bag carrier, which will assist people to carry purchased items more easily. The shopping bag carrier is intended for people who live in cities, students, and older people who don't have their own cars. The design process, which would include the conceptual design, development of parts, sub-assemblies, final assembly, and bill of materials. Many people who live in inner cities where keeping a vehicle is difficult are always confronted with the problem of carrying their purchased items from stores. Similar problem of transporting goods is faced by elderly people who live close to a shopping facility and students who live in dorms and people who don't have their own vehicle. The shopping bag carrier satisfies the need of this segment of society and assists them to bring home shopping goods with ease. The automated and motorized feature of this carrier also makes it attractive to disabled, injured consumers. One special feature of the shopping bag carrier is the tri-wheels, which will help to carry the goods up the stairs. Furthermore, people who have vehicles can also get advantage of the shopping bag carrier by not driving their own cars, which will help in reducing the environmental pollution and gas consumption. We have conducted a survey where we asked people leaving the supermarkets like Walmart and Target. And some of the questions were, if you live in a city or close to the university, would you buy a motorized carrier to help you carry your stuff? And the next question was, do you think it is helpful? And we got 137 responses and 85% of the people rated the project 9 out of 10. And they said that they would buy it, which is great. The shopping bag carrier, we have added a couple of features, and some of them are the motorized wheel, speed controller, battery powered, tri-wheels to climb the stairs. It is foldable, and it has a passenger platform, and the maximum speed is 3 miles per hour, and the maximum load is 308 pounds, and it has a telescopic handle. And now Abdullah will talk about the next part, which is the purchased parts.
So this is the schedule of the purchase parts. We have different items. Mainly it's about the wheels and battery and motor and gearbox and sprocket and bearings and going on. So each of our team members had to handle like different parts to purchase them from different websites. We found a very good website where you can find everything on it. It's MacMaster, and about the fabricated parts, we have 4 different parts: the case and passenger platform and the main shaft and shaft ABC. We worked with a workshop. It's called R.A.M machining. And even we are storing our items in the R.A.M machining workshop. Here is the purchase parts costs for each part. And the total was $519. And here's the fabricated parts cost. The rate was given by the workshop. It was $600 for the base and passenger platform and the tri-arm and main shaft and shaft ABC and the bearing housing. And now going on to the scope of work. We had for the scope of work we had to design different items to be done with the project. We had to design the enclosure, and we had to design the climbing wheels and trolley handle and passenger platform and the motor and gearing selection. For the shaft, here is one sample of our design. We had to design the shaft using different powers, and here is some equations that shows how we worked with the shafts, with designing the shafts. And this picture shows the pink color. The pink color is the main shaft, and the 3 blue color in the middle, they are the shaft A and B and C. And now going on, with Mansour Abdul Malik.
So this is the schedule that we followed in this semester. As you guys can see, we started our semester with reviewing the design calculation and drawings. We reviewed most of our calculations like the drive power, the climbing power, design shaft, and goes on. And we also reviewed our drawings, which we did in SolidWorks. And after that, we started with the fabrication, but sadly, we couldn't finish manufacturing every part. We just did some of them. Moreover, we didn't be able to go to the testing and construction. So as you guys can see, this is our schedule. We were catching up with most of the parts and we were up to time. So going on to the next slide. As you can see, this is one of the sub-assemblies of our project, shows every view of our case sub-assembly. These parts are manufactured and they are all assembled together through welding. As you guys can see, the welding sign in there, it shows like how deep the welding will be and what is the width of the welding too. You are going to see some of the parts later on this presentation, which we already manufactured. Going on to the next slide. These parts are the main shaft and the bearing housing, which we already manufactured. And now Abdurrahman will continue.
So now let's move to the real pictures. So as you can see, figure 1, this is the shaft ABC. And for the figure 2, the main shaft, which they are already made in the workshop. And these are the bearing house and bearing. But for the bearing, figure 4, that's a purchase part. And these, the tri-arms, which we can climb stairs for the figure 5. And for figure 6, the passenger platform. And these are a laser drawing, which means we already draw this in AutoCAD, then we cut it in the laser machine. And last, this is the base. And we also, it's a laser part. And this is the main assembly, where you can see like every part where it should be and how it's gonna look like. And now I'm gonna pass it to Othman.
The project statement. We have done 75% with our project, and we are up to date with our schedule. We have most of the parts ready. The only thing left at this time is ordering the motor, handle, and one laser part. We had to stop assembling and welding the final design due to the virus. We didn't face any problems while we were working on the previous steps. We are storing our parts in a workshop. It is located in Anaheim. Thank you everyone for listening.
Okay, thank you, group. Let's get started on the fifth project that we have today. This is called the Height Adjustable NICU Baby Crib. Now, a special hospital need was the target for this particular group. And what they found out was something which was not well advertised or not well known, but was a consistent problem that existed and has existed for a long time. So their design project would probably have, I'm pretty certain, an instant appeal for people who work in hospitals, especially in the pediatric ward. And for that, I'll let them explain what kind of a problem they solve for people in the medical profession, especially in medical wards. So for that, I'll turn you over first to the team leader, and that's Michael Russell. Take it away from here, Michael.
All right, great. Thanks for that introduction, Professor Sharma. So as Professor Sharma said, our project is the Height Adjustable NICU Baby Crib. As Sharma also said, my name is Michael Russell. I'm the team lead. Nicholas Carey is our co-team lead. Xavier Herrera-Keene is our safety steward. And Daniel Rosales is a team member who is going to kick us off here with the project background.
So the conception of this project arose from a nurse complaining of back pain due to the bending and lifting of infants to and from the standard medical crib. They stated that the pushing of this crib was quite difficult. And a NICU crib is basically a medical crib in which premature or ill newborn babies are placed for specialized care. Back to you, Michael.
All right, and then moving into the objectives for the crib. So as Daniel said, right, nurses have a lot of problem with back pain. So we wanted to design and build a NICU crib which had an adjustable deck height. So that would make it so they wouldn't have to bend over at awkward angles, again, causing them that back pain that they're complaining about. We also wanted to improve on current crib designs. So that meant adding a motorized deck tilt mechanism, right, which is a feature that cribs already have, but it's mechanical. So we wanted to electrify it. Then we wanted to integrate a crib drive mechanism, as also Daniel said, which would aid nurses in pushing the crib around because the cribs are heavy. Then we wanted to refine the drop door design, which would ease child compartment access. Again, just a daily use convenience improvement. And then most importantly, well, not most importantly, but also very importantly, is we wanted to manufacture it at a competitive price point, right? So we wanted to make sure that this crib could actually compete with other cribs on the market. So in order to do that, we knew that we had to construct the chassis in the top crib, which would consist of cutting and welding tubing together. Then we would need to manufacture the bracketry for all the crib components. This would involve water jetting the brackets, then water jetting them all together, or welding them all together. Then we need to assemble the tilt mechanism, the drive mechanism, the drop doors, and the lift mechanism separately, which would involve also cutting tubing and bolting the bracketry to those components, bolting our purchased components to those sub-assemblies, and also bench testing the components that we received. Then once those assemblies were tested, we would integrate the sub-assemblies, and then after all that was complete, we would test and verify that the design requirements were met that we originally said that we were going to meet. And moving into the contributions of each team member is Nicholas Carey.
So we try to divide each team member with equal workload. So first is Michael as the team lead. He also designed the tilting mechanism and the motor drive, which pushes the crib. And then there's me, the co-leader, who helped design the vertical lift alongside Xavier. And I designed the dropping door. For Xavier, he designed the actuators and the programming of them so they would sync together, as well as the vertical lift and the lower chassis. And then Daniel designed the upper chassis and child compartment, as long as helped me with the drop door. And then Xavier will discuss the final design.
Okay, and what lays before you is the culmination of work that's been done over the past about 7 months. So this is a rendered image of what we wanted to build this semester. On the left, you can see a top-down view, and on the right, from the bottom of the system. So starting off with, to actually make it height adjustable, we use linear actuators, which have potentiometer feedback, which is very important so they can move in sync with each other. We also have slide rails that allow for, to mitigate compliance in the system. And on the right is a lower chassis. It's quite modular and easy to build, so that made it easy for us. Next slide. So here is the wiring schematic that I had drawn out. Arduino is a really good programmable open source unit, but it can only output 50 milliamps of amperage. So you need intermediary things for it to trigger so it knows what to do. And to do this, you can use drivers. So the drivers that I use are controlled through pulse width modulation. So they're constantly sending voltage to the linear actuators, moving up and down with each other. Then on the right is a snippet of about 400 lines of code that I've written. Basically, all it's doing is taking the potentiometer feedback of every linear actuator and then having a datum, which is just an arbitrary linear actuator, and then constantly comparing them and adjusting voltage and speed in order to allow it to go up and down to sync without binding. Next slide.
Right, and then moving into some other ways that we're going to meet the objectives we said we would, right, is by electrifying that tilt mechanism that cribs already have. So here you can see on the left is the top view of what the crib would look like, and then bottom you have the mechanical system that actually tilts the crib up and down. And that's performed by also another linear actuator. The next design solution is the motor assist, and this is what's going to allow the nurses to push the crib around with much more ease, right? It's just a center-mounted Omni wheel with two brushed motors with gear reductions on them, and that'll push the crib at a reasonable walking speed.
And as far as design specs, the crib ended up measuring about 38 inches in length and 29 inches in width with a height of 40 inches. The actuators have a speed of around 0.5 inches per second for a total height adjustability of 12 inches.
And then onto design calculations. This was not too number heavy of a project, but as Michael stated above, the driving mechanism was calculated to travel at about 2.4 miles an hour, safe for hospitals. And then for the tilting mechanism, we needed a 45-degree tilt. And then so just simple geometry, we had to find a linkage to make that possible.
And here we can see some of our design drawings and our bill of materials. Can we go to the next slide to show them a bit more? And we're basically going to use these drawings to actually construct the sub-assemblies and individual parts. Next slide.
Okay, so here we actually have the construction of the linear actuators. On the right, you can see the dual channel drivers, term blocks, and also the Arduino wired up to the actuators. And then on the left, you can see a GIF that I've uploaded of them moving up and down in succinct with each other. It's hard to tell by the frame rate, but they're moving with each other. Here we have the lower chassis on the left, which has been cut and welded to our specifications. And then on the right is the upper chassis, child compartment as we call it. And then we also have a bunch of brackets that we needed to water jet and cut. So we have these components and probably about 60 other parts that we were going to weld together in order to assemble the whole system. And then here's just some more photos of us cutting and welding the system together.
As far as final prototype testing goes, the crib was to undergo a series of tests to validate its functionality and safety. For example, the height adjustability was to be examined through the testing of the actuators, and for the tilt mechanism, an analysis was going to be made to ensure that it elevated up to 45 degrees, and the motor-driven assist was to be tested to a similar environment to that of a hospital setting to ensure that the crib was mobile.
All right, and here we have the manufacturing schedule for the height adjustable NICU crib, right? This is a standard Gantt chart, very common way of managing projects. And here you can see the yellow highlighted line is where the project was put on halt, unfortunately. If you look at the top part of the Gantt chart, you can see we had preliminary steps such as reviewing design drawings, right, correcting any design flaws we saw, and just overall looking at the documentation we created last semester to make sure that this stuff could really be manufactured. Then moving on to the second half of the Gantt chart, you can see more integration related steps, right? And this is the stuff that we didn't really get to do so much because of, again, the project being put on hold. Moving on to the task assigning, right? This is how we manage the project in a more fine-tuned way, right? So here we actually had the task that each member was supposed to complete on a week-by-week basis. And we said who was assigned to the task. We would say if it was complete or in status or in progress. We also had the date assigned and the expected completion date, right? So these are just ways that we manage the project.
And then for the budget analysis, we were allocated a $2,000 credit. And so that became our budget. Listed in yellow were the parts that we managed to purchase. And then calculating all the other parts together, we came up with a total cost of around $1,100, which is well under budget for what we thought was going to be $2,000 total.
Right, and then moving into the current status of the crib. So as you guys saw in previous slides, right, the crib chassis and top crib have been welded and constructed. Our linear actuators, they move in concert with feedback control with each other, right, in bench testing. That's something that we're very proud of and was a big concern for us initially. So big shout out to Xavier for figuring that out. The bracketry for the crib and the tilt mechanism and the drive mechanism and the lift mechanisms, those have all been water jetted. And overall, as you saw in the Gantt chart, the project was on schedule, right? We were pretty much where we thought we were gonna be when everything got put on hold, and that's something we're pretty proud of.
So in assembling this, we noticed some future changes and redesigns that we thought we would like to add. Instead of having sliding rails, we thought we'd be using a UHMW plastic, which is meant for high abrasive areas and it has a very low COF. So just, so it would slide on the crib instead of slide rails. And then next slide, Michael. And then some other redesigns, the actuators aren't the quietest thing in the world, so maybe finding some way to reduce the noise by insulating them, redesigning a switch panel so the device can be used from both the front and the back of the instrument. And then, some limit switches for the tilt actuator, and maybe make it a little more child-friendly or eye-appealing.
All right, and then moving into our confidence of the project success. So overall, the crib was roughly 65% complete, with around 70% of the needed parts being purchased and about 60% of manufactured components actually being built. We estimate that about 40% of the assembly was complete, and really the biggest thing that was hindered by this is that the fasteners that we needed to really screw everything together, we did not get around to purchasing those before all of these projects were put on hold. So that really, we could have had a lot more stuff assembled if we had those key components. But as I said before, right, overall, the project was on schedule. We were where we thought we were going to be. There were no major issues that we encountered that we didn't feel we could solve within reason. So overall, we were really confident in the success of this project, and I think we definitely could have completed it, not only in the timeline that we said we would and in the budget, but also with having it meet the objectives that we said we were going to do. And that's something that I'm very proud of, and I'm very proud of the team for pulling off. So overall, I want to thank you guys for listening, and let us know if you have any questions.
Thank you, guys. Any questions come your way, Nancy?
Yes, we have one question. The question is that you mentioned the speed for the crib. What type of motor is used and how is it powered?
Okay. Yeah, so basically they're brushed DC motors. They're 550. They're classified as 550 motors. They're DC. And basically that is keyed into a planetary gear reduction, which spins the output shaft at 200 RPM. And that's what those calculations that Nick was talking about, right? Those drive to an omni wheel. And with some simple math, you can figure out an actual wheel speed for that. As far as powering them, we were going to use DC motor drivers powered off the Arduino, right? And those were going to send battery power. There would be a shared battery for all the electronics on the crib, and that would just divert battery power to the drive motors.
Okay. Any other questions, Nancy?
Yes. What is the price of the motor and how easy is it to service this device if a motor goes out?
It would be pretty easy, right? We designed the drive mechanism with serviceability in mind, certainly, right? There's a single bolt which holds the arm on for the drive motor. And then beyond that, with the loosening of a couple set screws, those two halves of the motor will separate, or the two halves of the arms will separate. And then from there, it's just two screws on the back of that plate, which pull that whole transmission and motor assembly off. And then from there, it's very simple to swap out those motors. And best of all, that motor size, that's a standard power drill motor size. Those things are ubiquitous, right? And you've got tons of manufacturers making those. So it's an easy part to get, it's a cheap part to get, and it's easy to access. So in terms of serviceability, I'd say it's pretty good. As far as cost of it, if I remember correctly, the motor and transmission assembly was $25 per side. So you could probably replace the motor for somewhere in the neighborhood of about 15 bucks, right? If I'm gauging the market correctly.
Thank you. There's one last question. The person asked, rusty parts seem unhygienic for the NICU. How would you prevent this if put into production?
Yeah, certainly. We definitely would have, right, none of the parts would have been untreated with paint, right? We would have painted everything, right, in order to ensure that parts weren't going to rust and make sure that, again, it's a safe environment for the child, right? You know, ideally, we would have powder coated too if we had enough time and money, right? Because that's a much more durable coating. But yeah, overall, no, untreated metal surfaces left free to rust would not have been in the final design at all.
Thank you, Michael.
Okay, thank you, Michael, and thank you, group. Okay, let's get started on the next project, which is the three-dimensional prosthetic hand. Now, prosthetics has gained popularity, over the last couple of decades, and prosthetic replacements are getting more and more commonplace. However, they come at a pretty steep price. This team has kind of worked at looking at a very practical solution for most people. And they have come up with this particular design, which they'll discuss in their presentation. And I'd like to invite Francisco Hernandez, the team leader, to start this off, please.
Hello and welcome everyone. Thank you for having us. So like Professor Sharma said, my name is Francisco Hernandez. I'm the team lead and my group is the 3D printed prosthetic hand. My teammates consist of Siegfried, Kareem, Miguel, and Dante. So just give you an overall overview of what exactly we did. It's a prosthetic hand composed of 3D printed parts as well as mechanical components such as servos and motors. The way we designed this hand is primarily using SolidWorks. We tried other programs such as Fusion 360 as well, but we just stick with SolidWorks because it was more convenient for us. And one thing I want to reiterate every time is that this project was based on a fabricate, test, redesign model. What that means is we will get a design, then we will print it, and then we will find the flaws and the mistakes and errors in that design. So we'd have to go back into the program, redesign it, print it again, etc. It was just a repetitive process, and that's how we were to complete most of our project. So let me tell you the big picture. Nowadays in today's market, prosthetic arms and hands are fairly high. They are very expensive, even just cosmetic hands that just stick to the nub of where you're missing your either your forearm or your hand. They range around from $2,500 for just cosmetically to up to even $50,000 for AI high-tech mechanical process parts. In the United States, there's roughly 50,000 new amputees per year. More than half of those are based on the arms from the forearm all the way to the hand to partial hand. And aside from financial struggles, amputees also face health and mental issues, such as not being able to perform day-to-day activities, as well as being seen and being stared at for not having a hand. So our main objectives for designing this printed hand is to be able to perform basic day-to-day functions. Some of those functions is basically just gripping and holding, such as holding a utensil, holding a cup, pulling and opening a door. And one of the main objectives we try to go forward is focus on students to being able to write either with a pencil or being able to write with an expo marker on a whiteboard. And as well as being cost efficient for primarily students, and students are faced with financial issues every day, such as rent or being able to pay tuition. We try to make this product as affordable as possible.
One quick thing here, Nancy, there's a lot of background noise. Would you know what that might be coming from? Nancy? Yeah. Okay. I was just hearing a lot of background noise in there, so I just wanted to know if you knew where that was coming from. And the request is that if anyone else is online, please just hold that noise for a little while till this presentation is over. Okay? Yeah. Sorry, Francisco, go ahead. Yeah.
No, it's fine, it's fine. Okay. So now I would like to pass the slide off to my team member, Dante. He will take over from now.
All right, I'm just gonna go over the scope of work that we had in mind. So we first started by completing several models on SolidWorks. And then from there, we also at the same time thought about our kinematic and stress analysis. After that was completed, then we moved on to our printing, as well as analyzing the tolerances for each of the individual pieces that we had. Aside from that, it really became more of a fabricate, test, replan project, and also implementing our non-print parts. And so here we have our work schedule. So essentially, we basically made time allocations for our three main pieces of our project. So for printing, coding, as well as our reprints and coding. Now, we basically set several days to finish up certain tasks out of these portions. And here we just wanted to show a front and back view of our completed SolidWorks assembly. And so essentially for our part list, we wanted to design it to as close to a hand as possible. So we essentially designed distal, middle, and proximal phalanxes, just like we would in a standard hand. And our base component was going to be our palm. Now, you're noticing as well as we have a thumb base 1 and 2. That's also our proximal phalanx as well as our piece for our thumb. And aside from that, just our finger subassembly, our Arduino kit that we use, separate boards, and then
Dante, please hold on for one little sec. I'm not too sure. Somebody is creating a lot of background noise, and we're not being able to listen to the speaker. So please, if you could carry your conversation either outside or somewhere else, I'd really appreciate it. Nancy, anything you think might be the source of that? Any predictions of that?
I'm not sure, but maybe we can move forward and hopefully we won't get interference.
Yeah, I think it might be from because it has to be from all the people who are sort of connected to this particular presentation. So please, if there's something happening,
if they could mute their mics until the next person's gonna speak, that would be great.
Okay. So if you're aware of that, please, if you can hold it for a little while, we'd really appreciate it. Sorry about that, Dante. I had to stop you, but you were almost getting unintelligible behind that noise. So please go ahead.
Okay, that's fine. So like I was saying, it was our Arduino kit, stepper motors, and then also our miscellaneous pieces, just like our screws and our wires after that. And now I just wanted to show you some of our schematics and drawings that we made on SolidWorks. So this is our distal phalanx that we pretty much use for every finger, including the thumb. This is our middle phalanx. Now, basically for our proximal phalanx as well, what we did, we took the design we have for our middle and just kind of extended it to kind of avoid taking too long on the process. And here we have what I was saying about the metacarpal piece that a thumb would have to improve the mobility of the thumb as well as its functionality. And this was our main subassembly that we pretty much use rinse and repeat for the rest of the hand. So this carried on from our pinky all the way to our index finger.
So our team decided to use Arduino along with the muscle sensors to control the movement of the prosthetic hand. We were able to develop a code that actuates, holds the grip, and then releases with a single input for each from the malware sensor. Simply by doing one muscle contract, the signal is sent from the muscle sensor to the Arduino, and then it's sent out from the Arduino to our output, which is a stepper motor. Here's a video to demonstrate how the code works. So when the stepper motor rotates clockwise, the hand will hold the grip, and then by giving another pulse to the muscle sensor, the stepper motor will rotate counterclockwise to release the grip. The delay between the two motors, the angle of rotation, and the speed could be adjusted as customers need. As for the initial cinematics, we decided to have the same design for all 5 fingers. Our prototype contained 2 stepper motors as shown in the video. The first stepper motor controls 3 fingers, which are the thumb, index, and middle finger. And the second stepper motor controls the ring and the little finger, or the pinky. As for the power source, we were debating whether to use a power bank with an output of 5 volts and of a capacity around 3,000 milliamps for each stepper motor, or we should be able to use AAA batteries, like rechargeable AAA batteries. Our team decided to use a braided fishing line to form a closed loop through each finger using channels through each piece, and then attach it to a thread to a pulley, which is controlled by the stepper motor as illustrated in the figure. Here's a simple demonstration of how the complete movement works for our design. So the top thread should be pulled by a stepper motor to form the contraction, and when it comes into the resting position, the bottom thread should be pulled. On our first prototype, we were able to fit the fishing thread as shown in the figure, and also we were able to fit the stepper motors inside the palm, and as for the Arduino kit and the breadboard, they were to fit inside the wrist. And as for our bill of materials, as you can see, we don't have that many parts. Mainly it was the Arduino kit that comes in with the breadboard and the stepper motors, the malware sensor, and the patches for the sensors, filament for printing, fishing thread for movement, and some miscellaneous parts such as wires, bolts, etc. And now I'm gonna pass it to Sig so he can explain for you guys the printing and the fabricated parts.
All right, so next we had to learn how to slice and 3D print the models that we created with SolidWorks. And how we did this was using a slicing software called Cura by Ultimaker. And so what Cura essentially does is converts polygon meshes from SolidWorks into G-code files, which is a programming language that tells the 3D printer what to do and how to print any given model that we plug into the program. So essentially it gives printers various set of directions, and these G-code files are also used in other things such as CNC machining. And so Cura has been very helpful in slicing models and creating aids for physical prints such as temperature control, print speeds, print resolution, infill, supports, and a multitude of other settings. And here we have an example of some of our fabricated parts. We have a mock-up of our printed hand with the exception of the thumb. Given our current pandemic, we weren't able to complete the printing. So we took various trials to ensure proper tolerances between each linkage due to variations in SolidWorks and the physical printer that we were using, which was an Ultimaker 3. And everything that we printed was sliced using the previously mentioned Cura. And so continuing on, we have a finger subassembly, which is fastened with a screw and nut just for mock-up purposes. Note the channels running through each linkage to allow for wires for the mechanism that Kareem had previously stated. And below that, we have stepper motor pulleys, which are needed to translate rotational movement into linear motion throughout the wire. And thanks to 3D printing, we can make adjustments in the diameters with these. And now we have an example of a mock-up of a single finger with the wires. So this allows us to see any adjustments that would be needed between each phalanx for mobility. And the video shows the contraction and retraction of how each of the fingers would move using wires that would be actuated by the stepper motor rotation. So we can see that upon retraction, the finger does not return properly, so readjustment was needed.
As far as for the testing procedures go, what we needed to make sure during the design and with the filament is to whether it can withstand a pressure, because in everyday use, our hands go with some type of pressure, little or extreme pressure. So we want to gauge it around like 5 to 7 pounds at least from the finger to the palm. Plus we want to make sure that it was able to freely rotate like Siegfried mentioned, and as well operate under the corresponding Arduino code that our team made as well. Then once we establish that each of the fingers do meet the requirements that we established with working with the code, as well as being durable, able to withstand the pressure as well, we were able to start doing our assembly and work with the functionality. With the functionality, it was crucial for us because we need to see what the limitations were with our design. My team like to think Cal State Forward team be able to provide us like the work sites to create a prosthetic hand with being able to use SolidWorks as well. And then a big thanks to Professor James for letting us use his 3D printing laboratory. With my team, we were able to meet up weekly into the lab and be able to simultaneously pass off notes or pass off on parts to continue printing, as well as to carry on for the next day as well. As far as for purchase parts, we did from the start of the winter season, we did get a head start by purchasing roughly about 50% of the parts already, spending into about 400 of our budget of 1,000 already.
we want to get ahead of schedule because, as Francisco stated, this is a fabricate, test, redesign process throughout the entire time. So we need to get the jump start on to make sure that each part will work towards the end.
Okay, thank you. Any questions for the group for the 3D prosthetic hand project? Let's get started. This particular project is a little different one, and it's based on educational experiences of most teachers. Usually what happens in the technology end of it, or in the science, technology, engineering, and mathematics area, teachers have a great challenge. They find that the students are not really engaged in it, and it becomes, there's always been a big problem. How do we teach them so that their interest level should be focused on the real thing, which will help them later in life? So high technology approach, like virtual reality and augmented reality, are the ways in which that could possibly be done. And to speak on that, on this particular study on augmented reality in smart interactive learning and manufacturing, Ibrahim Al-Jindan, and he'll introduce you to the topic. Ibrahim, please take over.
Good morning. Welcome to our presentation on augmented reality and smart interactive learning. My name is Ibrahim Al-Jindan. The team consists of Austin, Ali, and Yusuf. So augmented reality is a new technology that involves the overlay of computer graphics on the real world. Through the use of Unity software, we will be creating a virtual and interactive learning environment through AR, focused towards children to inspire them on the subject of engineering, as well as being more interested in the continuation of education. So traditional teaching methods leads to bored students. Several approaches have been taken on to address the problem of STEM learning, including direct instructions, flipped classrooms, self-learning, and so on. These existing methods suffer from different learning paces, lack of access to computers, and slow evolutions. Currently, there's a strong need for technology-integrated, innovative teaching solutions. So, like, have you ever got stuck assembling an item due to a complicated assembly manual? Kids don't get good complex assembly learning skills from an early age. Based on a paper by Dr. Chowdhury, e-learning teaching techniques have an advantage over traditional teaching techniques. The feedback from different user groups, students, researchers, teachers, and staff. The study showed that e-learning techniques attained high positive feedback as compared to traditional teaching methods for all the user categories. So our solution is making a video game platform that enables children to follow along and learn through a more interactive way. E-gaming is having a lot of success on the AR and VR field. Through a 3D environment, learning will be more hands-on and interactive, catching the attention of students. According to a study by Bloxham and Willingham, published by the Journal of Virtual Studies, students who experimented practical education using augmented reality improved their learning retention in English and math by 18%, motor and vehicle mechanics by 13%, and 7.7% in hair and beauty, and 2.9% in engineering. Teachers are a huge influence on a student's choice of subject matter on their decision to pursue a STEM career. Through traditional teaching methods, children can find themselves without focus and can be a challenge for teachers to engage them in learning. The lack of interaction between teachers and students both lead to bored and disengaged students. Between ages 12 and 13, students start to lose interest in science and other STEM subjects. Students have a perception of STEM subjects being either too difficult or too boring. Most children struggle to understand the importance of science because they cannot see the connection between what they learn in the classroom and what's happening in the real world. According to a recent study, the long-term impacts of teachers, only 5,839 of the 970,000 STEM interested students in the US, or just over one half of 1%, plan to major or pursue a career in math or science. So our project goals and objectives are: the main goal is to create an AR-enabled technological platform focused towards children that will engage them with a 3D immersive experience, changing the traditional teaching environment. Through the platform, we hope AR Assistant improves productivity and learning rate, demonstrate how it can be applied in other industries. So, our design specification is ease of use for all ages with a simple user interface and controls. The hardware needed must be easily accessible to the average consumer as well as the high-end customer. This ranges from everyday smartphones to the assembly instruction game needs to be fully interactive and help the user fulfill their goal. Software must be easy to extract to hardware devices and downloadable. So our approach at first was learning the concept and understanding the software at hand. Once we had made ground, it became a series of trial and error tests. Had to test multiple 3D models as well as different environments. Understand what each function of the software did and how exactly to do it. So Austin will now resume the presentation.
So for project activities, we created multiple models and assemblies for live testing within SolidWorks. As you can see on the right, we imported them into the Unity software to figure out which models were capable of being tracked using AR software. We also did lots of 3D printing for live testing. We needed to see what the pros and cons of each design we made are, such as if it's recognizable enough while still being simple. We did 2D and 3D tracking. On the top left here, we can see an example of 2D tracking within the Unity engine. 2D target images are uploaded to Vuforia software and tracked within Unity. On the right, we use model target generator software, which allows Unity to recognize real 3D objects by shape and structure using pre-existing 3D models such as SolidWorks. And then lastly, we used an object target, which is created by scanning a physical object using the Vuforia object scanner. There are also different target types, such as the cylinder targets, which recognizes images wrapped around objects of cylindrical shape, and multi-targets, which consist of multiple image targets in a geometric arrangement. So for outcome and results, we have some simple image tracking. So what it is, it represents images that can be detected and tracked by the Vuforia engine. On the left, we can see a 3D model applied to the target. On the right is a video playback being applied. This is 3D animation, which can be incorporated to give assembly steps one by one, or even given an exploded view of parts that have been manufactured and assembled already. For ground plate detection, it supports the detection and tracking of horizontal surfaces, and mid-plate anchoring and tracking gives users the option to place objects mid-air without a surface. So it allows mobility of user to explore any AR implemented objects and interact it with on a more intimate level compared to 2D image tracking. And here we have 3D model tracking. Model targets, these types of model targets enable apps built using Vuforia engine to recognize and track particular objects in the real world based on the shape of the object, such as being geometrically rigid and presenting a stable surface features. And then the application of any type of AR to the object, for example, information about maintenance can be applied. And there's more examples of how we can name each object based off the unique design of each model. So we can be able to identify it better. And here's AR versus traditional methods. So we can see how we can apply assembly into AR to demonstrate how it can be effective. Here we can see how easy it is to place each object into play in comparison to a drawing within SolidWorks. Using ground plane detection and model tracking increases the speed at which one complete a task. So for deliverables, we have an increase in productivity within the AR gaming platform compared to the traditional instructional textbook. Improvement of spatial awareness within assembly is apparent as a result of the immersive and interactive learning experience. Students increase their learning performance, engagement towards subjects, and the motivation to learn. Augmented reality inspires children to become interested in the STEM field and gives access to others as a different method of learning. The results of this study can very well be extrapolated to several other areas, including workforce training, quality inspection in manufacturing industries, and assistive technology training for people with disabilities. And for dissemination, we competed in the SRC. And that's it.
Okay, thank you.
Professor, we do have one question. The question is, did you use some sort of headset for the augmented reality?
Yeah, we had a VuFix augmented reality headset. It was just smart glasses. We were also looking to like VR devices to use for augmented reality, but a lot of them only had distance measuring instead of actual cameras pointed towards where we can have mixed reality. So yeah, we just used augmented reality glasses, and then we also used obviously Android and smartphones that had and we also bought headsets to apply to our smartphones.
Thank you, Austin.
Thank you.
Professor Sharma,
Uh-huh.
we have one question for the augmented reality group. What disciplines does this project draw from, assuming this is interdisciplinary? Did you work with people from different departments?
Oh, sorry. Okay. No, we worked on this completely by ourselves. We didn't work with any computer science majors or anything like that. It was just our group by ourselves. Yeah.
Okay, perfect. Thank you.
Okay, let's get back to the last project that we have. And this is quite an interesting project from the title. It says Smart and Mobile Bathing Apparatus. Now, one of the things that you probably noticed is that the homeless population, etc., present-day hygiene is of a major concern. And there are lots of restrictions to them. And what this particular group wanted to do was to provide some kind of a solution so that your proper hygiene could be created, the fully functioning in a fully functioning and a sustaining shower kind of a unit. So they'll explain to you what all the details of that are. And for that, I'd like to, the presentation, I believe, would be by 3 people. And I'd like to invite Mia Elias first to get this started. Take over, Mia.
Thank you, Professor Sharma. And before we begin, I'd actually like to thank all of you for sticking to the very end. I know it's probably been a very long morning. Without further ado, we are Team Simba, and I'll be introducing our project. It is called the Smart and Mobile Bathing Apparatus to Improve General Health and Hygiene. Today, I'll be accompanied by 2 of my team members, Min Huang and Sandy Hironima. Okay, as an introduction to Simba, this is a design and fabrication of a self-sustaining mobile bathing system. It's more formally known, the title is Smart and Mobile Bathing Apparatus, but we'll just refer to it as SMBA or Simba. It is a functioning system with off-grid capabilities, meaning it is does not require to be powered by any other external source or have a running water system. Everything is going to be self-sustained on this one card. And the purpose of this will be just to aim, especially during these critical times with viral outbreaks, we're aiming to minimize the spread of illnesses to provide a wider accessibility, specifically within the homeless population. Okay, as an example, in California, on Skid Row is a city well known in Los Angeles. It's a pretty small little block, a neighborhood, about 4.324 square miles. Within that that square mile radius, there's a population of about over 4,700 people. 2,700 of those people are actually unsheltered, meaning they are homeless, aren't able to live in a homeless shelter. They're just living on the street side by side, as you see in this picture. Especially during this time where we have this whole epidemic of like the coronavirus being spread and everything, if we revert to the CDC's recommendations, what they've recommended for us to do is just to practice social distancing and also follow proper prevention hygiene just to keep this under control. However, when we're looking specifically in highly dense populations where homeless is just like an epidemic that keeps rising, we have to look at the current resources available to the public. Next slide, please. Okay, so before we begin to actually design our project, we had to have an idea of what the available resources work currently. So far, so if we look at what the unsheltered population have, they have bathrooms, they have beaches, but those are limited to public facilities. And most of the time they're very limited for us. They're not able to bathe, they're not able to laundry. And then another option was the Lavame transporting bus, which is actually pretty useful, especially in these populations. However, due to city limits, they're not able to transport into all the locations that are available. Next slide, please. For this one, I'm just going to revert this back to our team member, Min Huang.
So for our project goals and objectives, there are a few things that we want to look at in regard to building our materials. So first, it's a manufactured, lightweight, self-sustaining bathing units, which we consider integrating heat transfer, fluid analysis, and material strength to studied in this project. So the purpose of heat transfer and fluids analysis are the fluid flow in the shower, and the heat transfer because we want to have some kind of a conduction where the user can have some kind of comfort when showering rather than just having cold running water, and intended for multi-scenario uses, which is mainly to aid hygienic limitation with rising homeless rates. Also for natural disaster, hurricanes, earthquake, where the accessibility in the environment is very limited to a certain square feet, so that this can fit into those natural disaster. So we custom design our filtration system, two-step filter. The goal is to recycle 50% of the water that we expended, which we want to beat the bust that we previously mentioned, lower the required maintenance, and sustaining the power supply, which we want to consider as a solar harvesting vessel. So the design specification, we varies in consideration between from 1 to 5, 1 being the highest we want to focus on, which is the cost, the demand, materials, and tools. With this, we want to consider the components analysis, follow the budget that was given to us by the department. Secondly, is this gonna function? And after we finish with the theoretical value, we move on to the physical. How will this function in the real world? Is this beneficial? Which this will be tested in our prototype. Third is our comfort. This, we have it as third because in the society, people want that comfort. But however, for us, this is not the necessity that we want to focus on. Moving on, energy, which is the power supply. How is this sustainable? How is this gonna recycle itself? Which we came up with solar energy. And fifth, which is the last one, is our target audience. Who do we targeting? Which is the homeless people, city, places like parks or natural disaster, where the government can have easy, accessible, and mass-produced. So design specification, of course, as we mentioned, limited in space. We want to keep our bathing stall compact to a 52-inch width and 34 depth standard apartment bathing stall. So this is a pretty small but enough room for one person to comfortably move around within the space. And the tire itself is a 15-inch tire, steel frame at the bottom, which can support 1,400 pounds or less. But we've tested it out and we can support a little bit more than that. So next is the filter cleanse to recycle water. Of course, we want to save as much of the water as we can due to the previous drought that we had back in California. With this, it involves some kind of chemical as well, but that is something that we want to focus on after the prototype itself is deemed to fit our criteria. moving on to the heating system, of course, the sun radiation, we want to utilize a copper heating resource, which later on we want to involve smart features to improve the quality, use quality control, which is the water indicator, heat indicator, automatic heat shut off. So this can be treated as an upgrade once we finish the prototype, if there's a chance. So project approach itself, we delegated a task to our subdivision, design, energy production and consumption, water filtration, fluid analysis, program electronic components. So this is split up between our teams, which they perfectly finish the products that we assigned to. We incorporate component analysis for the best material selection and design to accommodate the space and transportability. This is the model that we've done. The cart itself is the drawing based on the actual cart that we have at school. The stall itself is a design that we are following. We've finished installing majority of the walls, the inner layers. We finished everything except for assembling the pipe and the supply, that the power supply, which we weren't able to finish due to this epidemic. So the project activity itself is very simple in our side, which is 3D modeling, finite element analysis, manufacturing, and physical assembly of the housing design, which we, as a picture shown, we were in the process of doing. So moving on, I will hand it off to our team member, Sandy.
Thank you. We're going to switch over to deliverables. For deliverables, we have fully completed the body of the proposed apparatus in SolidWorks. As seen in our previous slides, we have a completed CAD model of the centrifugal two-step filter system. With the assistance of SolidWorks and ANSYS features, we were able to simulate the reaction of the apparatus with applied forces. This testing, as we first anticipated, was not possible. In order to have a good design for the two-step filtration system, the group formulated a MATLAB code for the fluid flow analysis and also for the heat application. Our group was able to create a CAD model of the heating system consistent of a copper rod and sun-ray heat. For dissemination, we presented at the SCUR in fall 2019 and presented to the Mujeres in Engineering Club in April 2020.
And I see there's one more question regarding water supply. How will they connect to water supply?
So for our system, because it's not connected to any other outer water supply, it's actually going to be just pre-supplied with the tank of a repump the expendable water through the filtration and then back up into the heating system.
Thank you, Mia.
Well, thank you. Well, that really puts us to an end to our projects in here. Nancy, I really want to thank you personally for helping out in this and making it all possible here. You're a great person to work with, and thank you very much for it. Guys, what I think in this is that, this whole showcase that we've had, although this has been sort of a partial one because of what we know, the good thing is that what you see coming together is what an engineer really does and what engineering is all about. Some of you who've been in my classes, and I've also said that engineering is of that profession which is made of practical people. They take science and put it to work for the benefit of society. And what you've shown in these projects is some of the ideas and practical solutions which are really, which is true engineering, which make science practical for everyone. All the projects that we've gone through, one after the other, has also taken an idea whose time probably has come, and you can solve some problem which is existent in society today. The other thing is, this is the only way in which you get real experience to develop a better understanding of what you are learning and really put it into practice. I would personally like to thank everybody who's involved first all the students who got together to make this happen, and then all the people who are behind the scenes who really made this whole thing possible. Because what you may hear me and you may hear Nancy, but there's a whole bunch of other people who are working behind and all other parallel tracks that we have who make all this possible. And thank you very, very much for being there. I think that does it for us. Again, my many thanks to all of you. And go out in this world after this, you'll be engineers and do good things, because I think that's what the next step is.